All right, so I'm going to get started because I've got a lot to cover today. So today we're going to be covering some ways of characterizing morphisms and objects in categories. But first of all, I'd like to mention some things that I forgot to mention in the previous lecture. One of them is one of the examples of categories would be the category prop. This is actually pretty important when you're considering the Curry-Howard isomorphism, for instance, which basically states that simply typed lambda calculus is essentially equivalent to propositional logic. The objects in this category are your logical propositions, and the morphisms are proofs that one proposition implies the other. And obviously you can have more than one proof, so you can be more than one morphism. Another thing I wanted to mention was the concept of a subcategory. It's an example of a construction that you might do on a category where you basically just take some subset of the objects and subset of the morphisms, but you in such a way that you still have all the composite morphisms so that it still remains a category. An example would be the category of finite sets, and then all of the morphisms between them. So we were just restricted the objects in set to just the sets with finite number of objects. That's all that I wanted to mention for that. So let's get going. I'm going to talk a quick review about some terms in set theory that you might have forgotten since you've taken your courses in set theory. If you recall from the assignment last week, I asked you to characterize all the functions between a set of 3 objects and a set of 2 objects. So let's take our 2 sets there. A is ABC and B is XY. Now, for the functions from A to B, you can essentially consider them as a triple. So A maps, your function will map A to some element in B, B to some element in B, and C to some element in B. So you can represent that as an ordered triple of elements in B. And similarly, if you're going in the reverse, you'd have ordered pairs of elements in A. Now, one thing to notice is right. So, as we saw, if the sets are different sizes, then if you're going from a larger set to a smaller set, you're going to have duplicates, and if you're going from a smaller set to a larger set, you're going to miss some. Now, there's 2 definitions for how this for these sort of properties. One is maybe of an injective function. And an injective function, you can think of it as sort of injecting the elements of the domain into the codomain. So that means that with this here, we've got 22 elements in the domain. If they map to the same element, that means they're equal. Now, I could have written a 2-way implication here, but the fact is that the other way around, if 2 elements are equal in the domain, then they have to map to the same thing in the codomain. That's actually a requirement of functions in general. So, yeah, I just wrote it as a 1-way implication here. And so, obviously, if for this to even be possible, the codomain has to have at least as many elements as the domain. Otherwise, you're going to be overlapping. There's going to be a duplication. Now, the surjective function, on the other hand, we have every element in the codomain has some element in the domain that maps to it. So we have here for every B in B there's an element A such that f of A equals B. And obviously for this to work, you have to have at least as many elements in the codomain as you must have at least as many elements in the domain as in the codomain. So yeah, and then we have bijective functions, which are the functions that are both injective and surjective. And pretty much the only way for this to work, based on what I said earlier, obviously, is for the sizes of the sets to be equal. And this is the definition of cardinality, right? You could just count the number of sets, but that doesn't really work for infinite sets, does it? So you have this definition with functions instead. Now, we're going to be generalizing these concepts to morphisms and categories in general. So the first generalization we'll talk about are monomorphisms. And they're injected. They are generalizations of injective functions. You could also say that a morphism is monic. So monic would be the adjective, right? And a monomorphism would be the noun, right? So the definition of a monomorphism is we have a morphism from X to Y here. That's a monomorphism if you have any two parallel morphisms. So for any object Z, and morphisms, any two morphisms G1 and G2 from Z to X. If we compose F after G1 and F after G2, if those two compositions are equal, then G1 has to be equal to G2. And similarly, if G1 is equal to G2, then the compositions have to be equal. So it's a two-way implication. Now, in order to understand how this is a generalization of a monomorphism, think about, I'm going to draw out our sets here. Here we go. We've got here's our Z, and we have some element in there. Here's our X and our Y. So we're going to think about what happens when a morphism fails to be injective, right? So if we have two elements that are mapping, that are duplicating, right? So they're mapping, both of these elements map to this one element in Y. So it's not an injective function. And if we have a function from Z to X, here's G1, right? And another function, G2, these are not equal. And yet, when we compose them with F over here, the composites are equal. So if the function fails to be injective, then you can have two morphisms, parallel morphisms that are not equal, and their composites with the non-injective function would end up being equal. So essentially what we've done here is, rather than, because, you know, category theory is all about ignoring sort of the internals of the objects that we're studying and only looking at the morphisms and how the morphisms behave under composition. So we've essentially, we're ignoring what's going on in the objects, and we've generalized this concept of injectivity to just how the injective functions work, the monomorphisms work under composition. Now, obviously, the monomorphisms in set are the injective functions. So let's move on to our generalization of surjective functions called epimorphisms, and the adjective version of this is epic. So epimorphisms the definition looks kind of similar, and they can be kind of hard to remember. What I like to do to remember them is just, work through this little example that I gave here, right? What happens if they fail to be injective or surjective? So in this case, you have two parallel morphisms, and you post-compose them with F, and if the compositions have to be equal if and only if the parallel morphisms are equal. And there's one final generalization we're going to talk about, an isomorphism. Now, in set, the isomorphisms are the bijective functions. right? And in set, it turns out that if a function is both monic, or sorry, injective and surjective, it's a bijection. That's not generally true though. So we're changing our definition. The definition is a little bit different for isomorphisms. Isomorphisms are morphisms that have an inverse. So you have this f to the negative 1 here. If you have a morphism from A to B, you have this inverse from B to A, and if you compose it, you get the identities. Now, isomorphisms are pretty important because of a concept called the principle of equivalence. So essentially, the principle of equivalence states that if we're talking about objects in a category, you can't really think of them as equal, right? Instead, you consider them to be equivalent, right, if there's an isomorphism between them. Now, I mentioned in the last lecture that we have the concept that the sets of morphisms between objects are sets, right? They're actually sets. So we can still consider morphisms to be equal to each other. And obviously, our definitions of monomorphisms, epimorphisms, and isomorphisms have relied on us saying, that the compositions are actually equal. But objects, we don't talk about them being equal. We have to say, okay, here's an actual isomorphism, and that makes them equivalent. And essentially, if there's an isomorphism between two objects, they have all the same structural properties, right? And we'll see some examples of those structural properties in a second here. So let's talk about some specific objects in our categories, right? The first I'll talk about is the terminal object. Now, this is a generalization of a singleton set, right? So if you think about a singleton set, it's a set with one element, and that means we can there's always a function from, actually there's functions between any sets. That's one thing. Set has a lot of morphisms in it. But there's exactly one function from any set to the singleton set. And there's only one way to do that. I mean, it's just the constant function that returns that one element. So the way we generalize this is we forget about what's going on inside the singleton set, and we just say the terminal object, which I'm going to denote here as 1, and there's a reason for that. By the way, a lot of texts will sometimes use 1 as the identity morphisms, but I've avoided that to avoid confusion. I use the ID, right? But there's a reason why I'm calling it 1 here. As you'll see, it behaves well with some other objects or constructions on objects that we'll talk about in a second. So the terminal object is defined by the property that every single object in the category has one and only one morphism going to it. So I've written here, we've got this T sub x is a morphism going from x to 1. And when you think about it, if you have two objects that have this property, I'll just draw it out. Actually, there's one thing to note. Let's draw a little diagram here. We've got A, B. Here's an arbitrary morphism, right? And here's our terminal object. And we have two arrows, one arrow. Right? So we know that from our category laws that there's an arrow that's the composition of these two, right? You can go from A to B and then B to 1. So we have T, B, F, that's an arrow, right? But we know from our definition of the terminal object that there can only be one arrow from A to 1. So that means that this actually has to equal T, A. So that's a law, and we say whenever this happens, when we draw a I'm going to call this is called a diagram, and I'll get into what the more rigorous definition of a diagram in a later lecture. But for now, just think of it as looking at a little piece of a category, right? So I'm just drawing two arbitrary objects and morphisms, right? And we're just looking at a little piece. There could be other objects, out here, right, that go around and stuff. But I'm not paying attention to those. I'm just looking at this. And we'll say that the diagram commutes whenever any two paths in the diagram are equal. So we have a path here and another path here, and they're equal, so the diagram commutes, right? And so if we have, suppose we have, another element over here. Let's just call it, I don't know, X. And there's one and only one morphism from each element too. And since we know the definition of a terminal object, it has to be that. So if we have two objects that both meet the definition of the terminal object, then this guy here is an isomorphism. Oh, I should mention there's ways of drawing isomorphisms and monomorphisms and epimorphisms in your diagrams. A monomorphism you draw with a little hook in your arrow. An epimorphism you draw with a double barbed arrow. And your isomorphism, you have a little tilde over it. So essentially, when we have two objects that meet the definition of the terminal object, that means that they're isomorphic. There's an isomorphism between them. And in fact, it's actually a unique isomorphism. So some examples of terminal objects in the categories that we've looked at so far. We have the singleton set, right? We looked at that. In fact, most other categories that have sets as objects, such as topological spaces, groups, monoids, vector spaces, the singleton sets or the corresponding, versions of the singleton sets in those categories act as the terminal object. Right, if you think about a monoid with one element, it has to be the identity element, and there's really not much you could do with it. So there's no other monoids other than the one with the identity element. In prop, it's the trivially true proposition. So this is, the arrows going to that would just be, you can imply true from anything, really, if you want. You can just ignore whatever the proposition is and just say, okay, true. This is the unit type in Haskell. It's a type with only one term, which is represented as a empty tuple. We have the trivial category, which is the category with one object and its identity morphism in cat. Those are some examples of that. Now, I mentioned every construction or definition will has a dual, right? And that's where the dual of a definition is the corresponding object with the same properties in the opposite category, right? With all the arrows reversed. So obviously the dual of the terminal object is the co-terminal object. It's more commonly called the initial object, but it can be kind of hard to remember with these definitions which is the non-co and which is the co version, but they relate to each other. So I'm calling this the terminal object rather than calling it the initial object and the other the co-initial object. So it's the dual of the terminal object. It's basically the same definition but with the arrows reversed. It's the object that has, for every other object in the category, there's exactly one morphism going from the initial object, the co-terminal object, to that object. And it's unique up to unique isomorphism. Some examples, the empty set. it's kind of hard to grasp at first, but there is actually a definition of an empty function. If you think about it, a function is just something that maps every element in a set to some other set. And if you have the empty set as your domain, there are no elements. So, you know, it's a function automatically, really. But this doesn't make sense to talk about more than one empty function, right? There's not really, and of course, you could never actually evaluate this function because what would you use as the argument? There's no elements in the empty set. The empty topological space, interestingly, topological spaces, the empty set is a topological space. But one, it's not quite the same thing as in our monoids groups and vector spaces, because you have to have, you know, your identities or your zero vectors in these. So it's actually the singleton sets again. And so that means that in these categories, the terminal and coterminal objects are the same object, and this is known as a zero object. And as a result, these categories behave a lot differently than some of the ones that we're going to be studying more closely in this class. But we have the trivially false proposition in prop. This is just essentially from falsehood you can deduce anything, the principle of explosion. The type void in Haskell is the initial object in our category of types in Haskell, and there is a corresponding function from the void to any other type, but of course you can't actually ever execute it. And you have the empty category in cat. Okay, so now let's talk about some more useful stuff, right? Products. Now, we've seen the product category already, right? And we saw the product of sets, right, which is just pairs of elements in our sets, right? So when we're generalizing this, we're going to call upon something called a universal property, and I'll get into that in a second. But here's essentially what the product looks like. If you have any two elements, A and B, in our category, we're going to write it as A times B, all right? And essentially, our product diagram is shaped like this. So the product has an arrow from the product to A and from the product to B. That's the product of A and B has these arrows, and they're called projection arrows. I'm going to draw the pi, whoops, that's A and pi B. Now, obviously, there's a lot of different objects in a category that could have this property where it has, you know, an arrow going to A and B. So we have to come up with the universal property. Essentially picks out a specific object that is sort of the most general of all of these objects. This is called a span, by the way, where you have an object with arrows going to two different objects. Now, if we have any other span, so let's say we have X here and another candidate for the project, so to speak. It's two arbitrary morphisms. If you have any other object like this, there has to exist a unique morphism going from X to the product. And I'm going to draw it as a dotted line to indicate that this morphism has to exist from the definition of the product. And essentially what this is, if we're going back to our sets, we're going to be doing this periodically where we go think about these definitions in terms of sets again. But and we're going to be doing, I'll show you some proofs involving the product, but it's important to remember that talking about these in terms of sets is really just a sanity check, right? You can do all these proofs just referring to the universal properties and the definitions in terms of the morphisms. So we're going to just call this F cross G. And essentially what this is, it's basically, if you consider these to be functions on sets, it's basically running these two functions in parallel, right? So, you know, instead of, and so this diagram commutes. That's the universal property. For any two functions go to A and B, there is a unique morphism from X. Yeah. There's a unique morphism from X to the product of A and B, such that this diagram commutes. So that means that we have F equals pi A after F cross G, right? So instead of going directly from X to A, you can go to the product and then project back to A. And similarly, G is equal to the projection B after X cross G. So that's our universal property. And oops. Now, like I said, similar to our terminal and coterminal objects, the product is unique up to unique isomorphism. So any other object that has this universal property, it's isomorphic to the actual product. And I'm going to be doing some proofs in a second involving that. Now, when you have the, you don't always have a product in a category. Sometimes some pairs of objects will have a product and others won't. But if we, in set, for example, the product of any two objects always exists. It's called the Cartesian product, right? And if we have the product of any two objects, you can just recursively construct it, add additional objects, so to get the product of any finite number of objects. And so we say that the category has all finite product. Now, one thing you may be thinking is, well, okay, so if we have, A cross B, A times B, and I want to include C in this product, I can just take this object and cross it times C. Well, the other thing you could do is do A times the product of B. Now, are these the same product? If you think about it in terms of sets, they should be, right? Because, I mean, they're just essentially triples of objects. But how do we know? We want to prove that these are essentially isomorphic, right? I'm going to just delete, clear this, make some room. So the way we're going to do this is, let's draw out our little diagram here. So we essentially want to find an isomorphism between these. So let's start by drawing our projections. And A, B. Sorry about that. Here's B. We're getting kind of complicated here. But this isn't too difficult, right? Because, as you'll see, our object down here has a morphism to A, and it has a morphism to B. Well, it has a morphism to C and a morphism to B, which means that instead of, we can draw a morphism going directly to the product B cross C. Similar for this one, we know there's a morphism going there because there's a morphism to A and a morphism to B if you compose these two projections, right? So now this object has a morphism to A through the composition of these two projections, and a morphism to B times C. So that means that there's a morphism going all the way up here. And similarly, this one has a morphism to A times B, this one that we constructed, and one to B, or to C, sorry. That's the composition of these. So this is another morphism going this way. All right. Now, so all we have to prove now is that these are inverses of each other. So that this morphism has this as an inverse, and that means that it's an isomorphism, and that means that these two objects are isomorphic, and they're essentially equivalent in our category. So how are we going to do that? Well, let's see here. We've got, oh boy, this is going to get messy. You know what? No, I'm not going to draw all these out because it's going to be basically unreadable. But essentially, when we drew these morphisms, you have your coherence laws, right, where they commute, diagrams commute. And if you want, you can verify this for yourself. I'll do another proof where we prove isomorphisms in a second. But let's move on. So, you know, let's take as a given that these that the product here is associative. Now, we're going to call a category that has all finite products and a terminal object a Cartesian category, named after the Cartesian product, which is named after Cartesian plane, named after Descartes, right, who invented the Cartesian plane. So the reason I'm including the terminal object in this definition is because I mentioned, right, that it behaves well in a certain way. So what do you think happens if we take A plus 1? You think this is going to be isomorphic to A? Well, if you think about it in terms of sets, right, this is just a set with one element, and these are pairs. And so you have an element from A, and the single element there. So these are all just going to look like, you know, pairs A, B, right, and so on. So there's essentially a one-to-one correspondence between the elements of A and the elements of A cross 1. So that makes sense, I think. It makes sense that they should be isomorphic, but let's prove it with just using the laws of the product and the terminal object. So here's A, here's 1. We've got our projections. Now, one thing to note here is that there's only one morphism going from any object to the terminal object. So instead of calling this the projection morphism, I'm just going to call that one, right? It's the same. It has to be the same based on the definition of the terminal object. And we have a morphism from A going to the terminal object. Let's see, here's pi. Okay. And this is just terminal object. Okay. So in order to prove that these two objects, A and A cross 1, are isomorphic, we already have a morphism going one way. We have to find an inverse to this projection morphism. So let's see, what could it be? Well, we have A has an identity, first of all, a morphism going from A to A, right? So that's one, that's a morphism going from A to A, and we have a morphism going to A to 1. That means that A is a candidate for the product of A cross 1, which means there's a morphism going that way. I'm going to call that, let's call it pi A inverse. We want to prove that these are actually inverses in a second. So, based on our definition of the universal property of the product, we know that pi A after pi A inverse is equal to the identity on A. So we got that part for free, right? And we know from the definition of the terminal object, and you could, and the universal property of the product, you could do either one, that terminal morphism from A to 1, whoops, that's not the right symbol, is equal to right. Now we want to prove essentially the other way, the other rule for the composition of inverses, which is that it should the composition in the other order should be the identity of the product here. How are we going to do that? Well, you'll notice that we can take this. How do we do this? Should have written this out beforehand. Well, all right, let's say okay. You know that this is okay. No, that's not gonna work. Shoot. I'm sorry, guys. Getting performance anxiety or something. You know what? I'll post this. I'll post the proof of this on the class site. I have it written down somewhere. The fact is, though, that man, I wish I could actually show you a completed proof of this, because your homework actually has a bunch of problems involving this. But let's move on. All right, so some examples of products would be the set of pairs. We looked at that one already. In prop, it's the conjunction, right? A and B, because if you have a proof of A from X and a proof of B from X, you can prove from X A and B, right? That's the universal definition. Topological spaces, product of topological spaces. And the type of pairs, obviously, that should make sense. We saw the product category already. And now, obviously, I mentioned all of these have terminal objects, so obviously all of these categories are Cartesian. Now let's talk about the dual of the product, the coproduct. And so this is basically the same thing as the product, but with the arrows reversed. So let's draw it out. And I'm going to use a plus sign to note this, and you should be figuring out that any object plus the initial object, 0, right, should be isomorphic to that object. And this diagram commutes, right? So how do we interpret this? Well, this is essentially the, if we're thinking about this in terms of sets, with the product, you could have a projection from the product to the original object, which is essentially just throwing out one side, right? It's just taking the left or the right side. With the coproduct, you're sort of injecting the elements of A or B into this thing. So it's kind of like a union, but it's actually a little bit more specific than a union. It's actually the disjoint union, which is essentially, if we have a set, A equals 1, 2, 3, and B equals 2, 3, 4. It's an ugly 3. Oh well. The union of these would just be 1, 2, 3, 4, but the disjoint union, we're going to sort of, actually, use the symbol for the disjoint union. It looks sort of like an upside down pie. We're going to label each of the elements with the set that they originally came from. And so these sort of injectors, right, would essentially map 1 to 1A, 2 to 2A, 3 to 3A, and from this set, 2 to 2B, 3 to 3B, and 4 to 4B, right? So you have, rather than considering the elements equal, it just duplicates them essentially. And this morphism that we get from the universal property, that's essentially, if we consider these our morphisms, general morphisms, that's essentially saying, okay, if the object in our coproduct came from A, we run G on it. If it came from B, we run F on it. And there's some corresponding examples. Obviously, so the coproduct is unique up to unique isomorphism, right? Just like the product. We have a category with an initial object and all finite coproducts is called a co-Cartesian category. Makes sense, right? And we're going to have the definition that if it's both Cartesian and co-Cartesian, it's bicartesian. Now, you might be wondering, since these constructions work well with ones and zeros and addition and multiplication, kind of, is it distributed? Are these two objects isomorphic? Can you distribute over these? Well, in set, it turns out you can do this, and that makes sense. But in general, it's not the case. In fact, you need to have some more restrictions on the category. But there is a morphism that goes that way. There's a canonical morphism. And one of your homework questions will ask you to find this morphism. All right, so some examples of coproducts. Disjoint union, talked about that. The disjunction, that's or in prop, right? Because if you have a function proving x from A and a function proving x from B, you can prove x from A or B, right? So in Haskell, it's this either type, and in general, when you're constructing a type definition, this bar here sort of lets you take the coproduct in your type definitions, right? It's not quite the same, but anyway. The direct sum in your vector spaces. Now this actually agrees with the direct product for finite dimensional vector spaces, but with infinite dimensional vector spaces, there's some more restrictions. The direct product requires that vectors be the linear combination of only finitely many of the basis vectors in either space, whereas the direct sum doesn't have that requirement. And if you think about what a coproduct of categories would be, it's sort of like just sticking the two categories next to each other in the same category, and there's no, and all the arrows, but there's no arrows going between the two elements. That's it, I believe. You know what? We have a little bit more time, so I'm going to look up that proof that elements are isomorphic. And it's getting kind of dark in my room. I can't really read these notes. Oops. All right. I'll just try to wing it. we know that oh, I remember. Okay, so let's essentially the identity for, if we compose it with, say, pi, it should equal pi, right? If we compose it with our terminal object, it should equal the terminal object. That we get for free, essentially, because of the definition of the terminal morphism. So let's do let's assume that is, let's do right. Right. So we take, if we were trying to prove that this morphism here is equal to the identity on the product of A times 1. So if it is, then this should just be equal to pi. Well, we know that composition is associative, so you just move the parentheses around, right? And we already proved that this is the identity on A, so this is just equal to pi. That's great. And that's essentially how you would do that. All right. Sorry about that, guys. I was blanking or something. So that's it. I'm going to open up questions. Any questions so far? Guess not. All right. So, oh, Keith, how are you? What's your question? I can't hear you, Keith. You want to just type it in the chat? Okay, so I'm saying that these morphisms are unique. Essentially, that if we have, I'll draw out the product diagram again. Here's F, here's G. Essentially, this morphism is unique in the sense that it's the only morphism that makes this diagram commute. If you switch out, if you would switch out these for different morphisms, then this would be this morphism that you get from the universal property would actually be different. And I guess another way of thinking about, or the other definition of uniqueness, I guess, would be that if there's two, in order to prove that it's unique, if there's two parallel morphisms that both make this diagram commute, they have to be the same morphism. All right, that's how you would generally prove uniqueness in an abstract algebra course or whatnot. Does that answer your question? Okay, great. All right, well, if there aren't any other questions, I'm going to end this class. The homework should be a little bit harder than it normally was because we're starting to get a little bit more abstract now, moving away from sets and whatnot. So please, if you have any trouble, don't hesitate to ask a question about it, and I'll do my best to help you out. So that's it. Thanks for coming, everyone.